certainly the first time for me, and maybe for several of you, and it's certainly the first time for IABSE to be doing an in-person meeting of this scale since the beginning of the lockdown. So how exciting is that? My name is Ian Firth. For those of you who don't know me, I'm the chair of the British group of IABSE. And welcome, guys. There's lots of room down the front, if any of you feel bold enough, and then fill in some gaps. And it's my great pleasure to welcome you to the Institution of Structural Engineers, with whom we have a very long-standing relationship, and it's very much a very friendly one. And we're very grateful to the institution for allowing us to hold our annual lecture here again, as we habitually do. Although for the last few years we've been online, as I say, it's a real pleasure to be back together in person, isn't it? So welcome to all of you. Tonight is a special occasion for a number of reasons. One, I mean, our annual lecture always is, and it's always a very high quality occasion. But tonight we have a speaker who I'll introduce to you formally in a moment, but who is about to become our new president. Tina Vejrum, who's sitting down here, is also a colleague of mine, and indeed of quite a number of us in the room here, I can see. It's a real pleasure to have you with us, Tina. I'll introduce you shortly. Just a few things before we get started. We do have the usual fire procedure, sort of housekeeping issue, just to point out if there is a fire alarm, which is very unlikely because there's no planned one, but if there is one, then we go out through the door you've come in, out from the front door, and please go to the gathering point at the end of the street here, number 42 Bastrop Street. So turn right out of the building, and the assembly point is down the end. That's very unlikely to happen, but just so you know, that's what we do. Please do also turn your mobile phones to silent or off. And having just said that, I've done this before and said that to people and forgotten to do it myself. And since unfortunately these days I carry two of the damn things, I need to do that twice. There we go. IABSE, some of you may not know us, the International Association for Bridge and Structural Engineering. As the name implies, it's international. It covers all aspects of structural engineering, all materials, all types, all sorts of things. Some people think it's mainly about bridges, and if you listen to tonight's lecture, you could be forgiven to think that it was all about bridges. The majority of the audience here tonight will be mainly bridge people, but it's not by any means just about bridges. So it's all sorts of things. And we, the British group, are very active. There's lots of things happening. This is one of our main events of the year. We also do the Mill Medal lecture, which also takes place here. And there's a lot of stuff happening. And I can warmly recommend, please, that you go to our website to see what's happening, iabse.org.uk. If you just go to iabse.org, you go to the headquarters website, the headquarters being in Zurich, but add the .uk and you come to the British group, and you'll see there what we're up to. There's an awful lot there. You can also see past lectures which have been recorded and so on. This lecture tonight is going to be recorded, so it will find its way there in due course. Being an international organization, of course, we have a lot of international events. And some of us, many of us, I suspect, in this room, will be heading to Prague next week for the next international conference, which is in Prague. Good again to be back to full sort of face-to-face. And then later in the year, in September, or is it October? I can't remember now. We're in Nanjing in China. We'll see how that works out. And just as something for your advance notice, this is a note for your long-term diaries. For May, or at least the spring 2024, we here in the UK are planning to hold an international event. The symposium in 2024, we hope, will be here in the UK. Venue to be decided fairly soon, so we'll watch this space. Much interest in that. I hope all of you will be thinking about what you can contribute to that event. I'm sure you'll all be there. Okay. That, I think, is all I need to do by way of introduction of the sort of events. But tonight we have the lecture, as you've heard, and after the lecture, just briefly, many of you, I hope, are going to join us on the river. We've got dinner tonight. Our annual dinner will be on the boat, and so we leave from here. There's a coach which will be leaving from outside. You turn left and left again. There'll be a coach there for those of you who are signed up, and it is only for those who are signed up. Please don't you know, what do you call them? Stowaways, there's a good one, Angus, thank you. No stowaways, please. And we depart from it at 8 o'clock from Westminster Pier. So if you've got anybody joining you, make sure they're there probably by about 1:45. And we'll be back by 1:15. And we're very, very grateful to our sponsors for the dinner. Teufelberger Red Ale. I find it still a bit of a mouthful. David's giggling in the front here because I've known him as Red Ale for as long as for a long time. Actually, I've known you for longer than the time you've been there. But anyway, really grateful to them for sponsoring our dinner. We have representatives here with us tonight. They'll be speaking to us, I hope, when we're on the boat. There's a banner there from them. So thank you so much for that, sponsoring the dinner. So it comes to talking about Tina. I first met Tina on the Stonecutters Bridge site in Hong Kong back in, I don't know, 2006 or 7 or something like that. It's a while ago. Tina's a colleague from COE and is currently vice president with a very big portfolio for all the sort of international bridges, the big ones, and you'll be hearing about some of those tonight. She did tell me a little earlier that she's delighted that she's going to be moving back into more of the technical role, leaving behind the vice president role in a few months' time, which will be great to get back into the bit of engineering, get the calculator out again. So she will be senior technical director. So I think, as I say, I've known her since around about that time. I have a special, some of you will know, the Stonecutters Bridge is very close to my heart. She might tell you why later on in the talk. But she did her degree at the Technical University of Copenhagen, DTU in Lyngby in Copenhagen, did a PhD with Niels Gimsing, who some of you will know, certainly by name, one of the great sort of long-span bridge gurus. Can I say the 20th century? He's still with us, but he's one of those big names, isn't he? For those of you who are long-span bridge people. So did a PhD with Niels and then joined COE. And the very first project she worked on was the Storebelt Bridge, the Great Belt East Bridge, the big suspension bridge. One of So without further ado, Tina, I'm going to ask you to come and deliver your lecture entitled From Stonecutters to Nakele and the Future of Floating Bridges. Tina.
Well, thank you very much for that introduction, Ian, and thanks to the entire British group of IABSE for inviting me. And I was so fortunate to attend part of the annual General Assembly just before, and I have to say I have to congratulate the British group of IABSE for being so active and for having so many meaningful activities. It is really an inspiration for, I think, all national groups throughout the IABSE community. So please keep doing what you're doing, and we look forward to 2024. It's already in the calendar. I would also say this is really a huge honor to be here. As I understand, it's the first face-to-face opportunity for a very long period of time. It's been a while where we have not been able to meet face-to-face. So if I mess a little bit around with the technical stuff or something, then please bear with me, because we got so used to the virtual or the hybrid format, which has served us well. And it has helped keeping us together during the lockdown and working from home. I'm going to speak about these fantastic bridges and throw in a few more of my personal favorites. I mean, it's a selection, there's so many, and I'm sure each of us has our personal favorites. So here are a couple of mine. And I'll also try to put some of my IABSE involvement into the pot. So hopefully you can see that there are some synergies, and for me personally, it has been very meaningful being so involved with IABSE throughout the years. So I can only encourage you to do the same, and you already are, but to do even more. So adding to what Ian said, I tried to list what I've done with COE and what I've done with the IABSE, and it seems a little bit out of balance. Time-wise, of course, it isn't. I didn't list to see the multitude of opportunity offered in IABSE. And as many of you would probably have done, I also started with involvement with the technical activities with the Working Commission 2, as it was back then, and quite quickly got dragged into a very interesting initiative, a task group that was set up to define a new strategy for IABSE, and Professor David Nethercutt, sitting here on the second row, was an instrumental part of that group, so I'll touch a bit on that. I have, until last week, I was also chair of the Danish group. I have stepped down now because with my new sort of position as incoming president, there is a slight conflict of interest, and definitely with Ian overseeing the activities in the national groups, I don't dare to be the chair anymore. So that was a bit about my activities with the IABSE, and as Ian said in his introduction, it is really a very interesting and very valuable aspect. What I like about it is that it embraces all aspects of structural engineering, all types of structures and materials, and all phases or all phases of the life of a structure, from initial ideas until rehabilitation and eventually demolition. It deals with historical structures as well. So there's really something for everybody and for every taste. We're close to 3,000 members in over 100 countries, and we'll soon be celebrating our 100 years anniversary. So I think there's a lot to celebrate in the association. So why are structures so important? And as Ian quite rightly said, tonight we're probably mainly focusing on the B, on the bridges, but the S&E structural engineering is equally important in the association. So it just happened to be bridges tonight. And I have picked a few examples, I would say, of historical bridges or structures that I think just illustrates why structures, they have this potential to become so iconic. And Pont du Gard is, for me, a good example. It was built more than 2,000 years ago as an aqueduct, and it served as an aqueduct transporting water for 500 years. And then it fell into sort of disrepair, and it wasn't really used until 270 years ago, when it was upgraded with a road. As you can see behind sort of the lower level of arches, there is actually a road now passing across the river. So I think that's a good illustration of how old structures can be put into new use and become a very meaningful part of current infrastructure. Another one I like is the Forth Rail Bridge in Scotland, which is, as the name says, it's carrying a railway. It's a cantilever truss, and it was the longest span. It was the world record for over 25 years. I think that is amazing. I mean, considering today the world records, that's suspension bridges, but back then it was actually a structure like this that was able to hold the world record for such a long period of time. It is a massive structure, but I think it's beautiful in its own way, because it really, the form illustrates the function, and you can also read how it was built out of this structure. So I think it is a wonderful example of a structure where somebody put a lot of effort and sort of all their skills into it, and it's still in operation. I mean, over 130 years still in operation. So I think these are really great examples for inspiration. So now none of these bridges had any Danish input, or at least very little. So how did Denmark become a nation of bridge builders? And to tell you the truth, I actually think it started with us being seafarers. And I couldn't resist the temptation, being in London tonight, to throw in a picture of a Viking ship, or at least a replica of one. And perhaps I should apologize for the mess that we caused in the process. We're still sailing the seven seas. This is one of the biggest container ships at the moment. It's owned by Maersk Line, which is a Danish shipping company. So somehow it is linked, and it is, of course, because our country consists of over 400 islands. And there has always been a need to cross the sea or cross obstacles somehow. So I think it's fair to say we started as seafarers, but we became bridge builders. I would also note that it's a very flat country. the highest natural point in our country is 170 meters above the sea. So we are very concerned with sort of rising sea levels and the effects of climate change. So that is something that feels very real for a country with that topology. We do celebrate our heritage, and here is a selection of the current Danish banknotes. So on one side, it has artifacts from Stone Age and the Bronze Age and the Iron Age. And on the other side, it has important Danish bridges. And you will see sort of on the biggest bill, we also have the biggest bridge, that is the Great Belt Bridge. So I think it's interesting to see actually that the entire collection of banknotes has a bridge on them. So it just illustrates how important it is for us. So that takes me to the Great Belt link, and I understand there are actually people in the audience who have worked on it. So if you have some comments, then please add your story. This was the first project I worked on when I joined COBE in the mid-90s. It was just sort of the last phase of Great Belt, and during construction, after the main span had been closed, it was observed that it suffered from vortex shedding, and we had hoped that when the asphalt was put on, it would dampen it, but it didn't. So I was part of the team that had to, in all haste, retrofit it with guide vanes, so these little devices underneath the deck that suppresses the vortex shedding. And according to our aerodynamic specialist, it is now as stable as an eye surgeon's hand. So it is, it did work, but it was quite an interesting piece of research we put into it, because there was an expectation that it would suffer from vortex shedding. But again, why fit something that's not needed? It's waste of material and it needs maintenance. So I think there was some sensible decisions behind waiting. Yeah, if you're interested in cycling, then I would encourage you to keep an eye out for this year's Tour de France, because the Grand Départ will be from Copenhagen, and the second stage will pass over the Great Belt Bridge. We'll close it. It's one of the most important pieces of infrastructure in our country, but we will close it for the Tour de France. So on the 2nd of July, the peloton will pass on the bridge, and if we have weather like today, it will just be an amazing day. Another early career project that made a huge impression on me was the Lionsgate rehabilitation project in Vancouver. I was so fortunate to be seconded to Buckland and Taylor when they joined the COBE group, and they were working on this amazing project. So a complete deck replacement of a suspension bridge, which by then was 60 years old. And it was so carefully planned that they could cut out sections during night, fit the new section, which has a slightly different cross-section, and then it would be open to traffic the following morning. Really, it was just like a clockwork. And I think, so with our aging infrastructure, we'll see a lot more projects like that. There is a need to upgrade our existing infrastructure and to get the most out of it. Upgrade it to new use, to increased loadings, or whatever is needed. But I think this is a great example of how it can be done. And then, as Ian said, let's move to Stone. I think this is sort of a favorite that we have in common. For me personally, if I was to mention only one project, this would be sort of the bridge I would highlight. I worked on the project for 10 years, so it has made a huge impact on my professional career. It started during the design competition, and I'll come back to who won that design competition. You probably have guessed by now. But I was sort of on the other side, part of the team, assessing the entries in the design competition. So it was really interesting comparing the different schemes and seeing the imagination that the teams put forward in that design competition. I think there were 25 entries. And then moved on to be involved in the detailed design and finishing with 3 years on the construction side. And needless to say, I mean, the lessons learned and the feedback you get as a young engineer working on a construction site, you just can't pay it with money. It's so valuable. And I would encourage everybody to have that experience. So the parties involved. And we should probably start from from the bottom, because the winner of the design team was a group with Halcrow, Flint and Neil Partnership, as they were called back then, Smitty from Shanghai, and then Dissing and Weitling Architects came up with a stunning design. And what is built today is very loyal to that design. I would also say here's a small link back to the Danish seafarers, because I got this picture from a captain from the Maersk shipping company the first time he passed under the bridge after it opened to traffic. So that was quite nice to see what it looks like from that angle. What is special about stonecutters? I think one thing to highlight is the prominent location. You can see it's right at downtown Hong Kong, so it's clearly visible from many areas on Hong Kong Island and the Victoria Harbour area. It's prone to typhoons. Basically, it will get a direct hit, and it has been tested full scale by direct hits of typhoons. There's nothing to give just a little bit of slack on the wind lows. It is spanning across the entrance to one of the busiest container ports in the world. So closing it during construction or during lifting of deck segments was not really an option. So that was also part of, I think, the decisions that the design team made, or the ones who came up with the concept that a cable stayed bridge would be a really good solution for this location. And in order to span the entire entrance to the container port, it required what was at that time a record span. So Hong Kong is prone to typhoons, as we heard a couple of times. What you see here is a track of Typhoon York. And what the containers that have fallen down there, it's not even the result of Typhoon York. That was just a small typhoon that happened while I was there. And driving home one day, we saw, oops, there was some effects of that typhoon. So it was also appreciated that perhaps the design codes in Hong Kong were not fully able to provide what was needed as basis for a design of a record cable stayed bridge. So there were lots of research put into measuring the wind climate at that particular site. We got a lot of wind data from the Ting Ma Bridge that you can see in the middle photo. There was terrain models tested in the wind tunnel, and there was also a mast with lots of equipment put on site, a 50-meter high mast. Of course, it couldn't be used in the design as such, but it could be used further down the road for verification of what we had done. And one of the key aspects that came out of it, and it was a combination of the characteristics of the wind, because it was very turbulent at that place. There are some quite high hills, definitely higher than what we have in Denmark, 500-meter high hills nearby. And it was extremely turbulent, and the vertical component of the turbulence played a decisive factor actually in the wind loadings on the deck. And that was, of course, a combination of the layout of the deck and the characteristics of the wind. And we're kind of taking that learning with us in other designs of twin decks, as we'll see a little later. So it was also tested, it went through substantial wind tunnel testing at different scales. You can see at the upper right pictures of a fairly large section model that was tested in Canada. And it was because that it was appreciated during the design process that the scale effects were significant. So the Reynolds number effects in the testing was something that needed to be taken into account. And those learnings have been transferred to design of bridge decks like the Chanakila twin deck as well. So I would say there's a lot of legacy from stonecutters that is being used very actively in our ongoing bridge designs today. So then I came back from stonecutters in 2008, and it was a little bit of a difficult transition working on a site and then getting back into the office. I have to say, it is so enjoyable to be able to go out there and look at the things and discuss with the contractor and find solutions together. But I moved back in 2008, and then I mainly focused on project management. And I haven't listed the projects here, but I worked with a couple of you in the audience on some of them. tender designs, detailed designs, checks, and the first concepts for floating bridges started at that point in time. And then I moved into line management as well. And during the same period of time, I became very active with IABSE, mainly in the first instance thanks to COVI's CEO at that point in time, Klaus Ostenfeld, himself being a former president of IABSE and being very focused on technical excellence. And I think that that's very much the DNA that runs through the company. And through Flint and Needle Partnership, who joined us, and Buckland and Taylor, who joined us. I think it's very much driven by that wish to push sort of the innovations and the boundaries of technology. So Klaus introduced me to IABSE, and quite quickly in 2011, this group of people were entrusted with the responsibility of coming up with a new strategy for IABSE, which was at that point in time losing membership. And as you can see there, with Klaus being at the back, being a former president, at that time the current president was Pete Popovich standing in the front. And then there are 4 coming presidents in the picture. So David on the picture on the left took over after Pete. And then we had Fernando Branco standing to the right of David. And our current president, Professor Yao Yunge from Shanghai. And then standing at the back, I'll be taking over in November. So I think this just demonstrates sort of how deeply anchored this new strategy has been ever since, because all the following presidents have been part of it, and we have a lot of ownership for it and put so much effort into it. So I would say it's good to see that the leadership of IABSE stays true to what was agreed back then. Another really meaningful experience for me was to be part of organizing the Geneva conference in 2015. And perhaps a little bit similar to the Bath conference that was organized with very short notice here in the UK a few years back. The Geneva conference also had very little lead-in time because there was another arrangement that didn't work out. And the group behind it decided to try out some new formats and to try to do things in a more sort of embracing way and involve the audience a bit more instead of having this typical one-way communication that we're so used to from conferences. So I hope in the 24 conference here in the UK we see even more of that implemented. I think Bath was really a legacy of some of the ideas from Geneva. So I would be very pleased to see that you try some different formats. And I mean, everything doesn't have to be perfect. It's about trying something that's meaningful and makes people engage and want to contribute. Then the next steps for me, I became vice president with COVI in 2015 and a member of the foundation. COVI is owned by a foundation and by the employees. So the foundation supports research. We have quite large donations every year to various types of research, not only within the company, it's also sort of completely independent from the company. So that's a very good way to supplement, I feel, what I do in my daily work. And then with the IABSE, I've been with the executive committee since 2016, and then president-elect as it was from October last year. And I look forward to collaborate with Yao Yunge on sort of this transition period and make sure that all the good initiatives that have been started and that they also implemented and carried through. So it's a great honor. How are we looking for time, Ian? Are we okay? Good, then let's move on to some of these record spans, because during this period of time, we could see a global trend that the crossings that were sort of put forward and proposed were becoming more and more challenging. Deeper waters to cross, longer crossings, and if they're deep and long, they typically require longer spans. In very harsh environments, and consider, as I said before, the effects of climate change is also something that is impacting our structures. The extreme weather is becoming more and more extreme, and the patterns of the typhoons seem to change. So there are lots of things to take into account if we want to ensure that our structures have a service life 100 years. And actually, we also see requirements beyond 100 years. 200 years was the required design life for the Messina Strait Bridge. There's also a push for shorter construction schedules, quite often because these projects are procured in a concession fashion. So there is a push to open them to traffic and start getting income as quickly as possible. And then, of course, very, very important sustainability, to make sure that when we invest so much of society's money, that we do it in a sustainable way. So in order to do that, we need to come up with new technology, and we need to apply technology that may already be known in other industries, but we need to bring it into structural engineering. We need to think sustainability, the benefits of digitalization, so we work really efficiently. And we need to design for the future. So it's about imagining what could be the future requirements for this infrastructure. How can we make sure that it is future-proof? And in order to do that, it's really important that all the stakeholders collaborate. We need to pull in the same direction in order to be successful. And this is teamwork. I mean, this is not something that one single person can claim to do. So even though we all have a favorite bridge, I don't think any of us can say this is my bridge. Those days are over. It's really teamwork. So let's move on to Çanakkale. So first of all, the location. It's at there's, perhaps you can see the circle blinking down there. The blue dot in the middle, that's the Sea of Marmara, and up towards the upper right, you have the Bosporus Strait with the 3 Bosporus bridges. One of them, the most recent one, is shown there, Bosporus 3. To the right, to the east, you have the Osman Gazi Bridge, the Izmit Bay crossing. And then to close the circle and this motorway around the Sea of Marmara, there was a missing link, and that was the crossing of the Dardanelles Strait. So that is the Çanakkale Bridge. So this slide is very busy, but it is really to illustrate to you that it's a red part that is the important thing. The little green bridge there is just a component. So, I mean, even though it can be very, very meaningful and challenging for bridge engineers like us to design a world record span, it's not a goal in its own right. It is because it's part of something bigger. So in this case, it's part of an 85 kilometers highway that basically closes the loop and saves a lot of traveling time around the Sea of Marmara. So what is characteristic of this site? Well, you look at the location of it. On one side you have Europe, on the other side Asia. So there's a fault line in the middle of the strait. The seismic activity is not quite as big as on the Osman Gazi Bridge, but it is quite high seismic loading. And the location near sort of the east end of the Mediterranean Sea means that there are high wind loads. As you would imagine, there's a significant shipping traffic through that strait because it's the only route from the Mediterranean through the Dardanelles, Sea of Marmara, Bosporus, and then to the Black Sea. So there's a lot of shipping traffic, both container ships and cruise ships. There's a lot of symbolism in the design of Çanakkale, and that was there when COVID got involved in the detailed design. So there were some very strict requirements to the design. It is a historical site for the Turkish people, and therefore in 1915 it sort of reflects on an important battle in World War I. And it took place on the 18th of March, therefore the pylons are 318 meters tall. The groundbreaking ceremony was on the 18th of March. And the opening to traffic was on the 18th of March. So the symbolism is important. And then the famous main span, 2023, that's quite an odd number. But it is because the Turkish Republic celebrates its 100 years anniversary in 2023. And originally it was intended that the bridge wouldn't open until next year, but construction was so fast and was accelerated, so it actually opened a month ago. So, in case you wonder sort of what is in it, then that's the explanation. Here are the stakeholders, and it is a very international project. The owner is the Turkish Ministry of Transport, and then there is a concessionaire and the contractor, consisting of 2 Turkish contractors and 2 Korean contractors. Delem, Limak, SK, and IABSE. So that was the contractor joint venture. And then COWI was responsible for detailed design together with Korean subconsultant PEC. And they had developed the tender design, so we didn't get involved until it was actually won. Arup, together with Ås Jacobsen from Norway, were responsible for the independent design checking. And then just to illustrate sort of how complex it is, financing comes from 24 different banks from 10 different countries. So it is a very international project indeed. The technical challenges include the ground conditions and not super favorable for such a big bridge, and we had to make some modifications. The seismic activity, as I already mentioned, live loads, I mean, if you have such a long loaded length, then the live load becomes very significant. Wind climate dominated large portions of the design of the superstructure. And of course, such a big bridge, just absorbing the movement was a challenge. So there were several hydraulic devices installed on the bridge in order to sort of control the movements. And then both the design schedule and the construction schedule were very aggressive. So in order to meet such an optimistic design schedule, I'll show you what it is in a second. We had to really optimize digital solutions and working efficiently with the data and not transferring data manually from one tool to another tool. So in the company, we have our integrated bridge design and analysis system where basically everything takes place inside one big global model. It has everything, including the construction sequences. So the way we manage it, instead of having a big sort of heavy model to work with, we have these building blocks. So we have shell models of the detail that we're currently interested in, and then we can switch them on and off depending on whether we are looking at the substructures or the superstructure. So in that way, we could optimize the analysis. And also, we included the fatigue model in the global model. And that was actually based on a learning we took away from the Messina Strait Bridge, which I haven't talked a lot about yet, but I'll come back to it. That's actually a triple box arrangement because it carries both rail and road. And during the design of the Messina Bridge back in maybe 15 years ago, it was noticed that it was very important to have the global effects included in the fatigue stresses, in the stress ranges. And we wanted to do that because we didn't want to be overly conservative. I mean, you can combine worst with worst, but then you're over-designing. And as you all know, the bridge deck is carried by the hangars, the cables, the main cables, and the tower will ultimately take the compression force. So any additional weight in the deck, it will just have a knock-on effect on all the other structural components. So therefore, a lot of effort was put into really optimizing the bridge deck. One of the first things the team did when they started looking at the tender design, it was to look at the anchor block location because the soil was really not good for such huge structures, subject to large horizontal loads. So they decided to move the anchor blocks further away. And since we couldn't touch the length of the main span, then basically the side spans became longer. And they became so long that it was no longer possible to have a traditional saddle at the side span piers. There was a need for a holding down arrangement. So that was a new feature that was introduced in order to make it possible to move the anchor blocks further back. Seismic design, nothing really special there. It's done the way you would expect it to be done with a number of various time histories. And Of course, it was made a little bit complicated by having these non-linear elements, the hydraulic buffers at the towers and the soil structure interaction and the wind bearings. But it was all fairly automated and made in a way that it was quite efficient. In the beginning, when setting up the design basis, we put a lot of effort into reviewing the live loads, because basically our codes, they're not really set up for such a long loaded length. So we looked into calibrating and seeing whether there could be a little bit of saving on the live loads, and that was possible. It was not a lot, but still worth taking into account because of that knock-on effect on all the other structural elements. And of course, all of that was in close dialogue with the independent design checker and with the owner. Ship collision was a major issue. As you can see there, the green lines, that's a plot of the AIS data from actual ships sailing there in the Strait of the Dardanelles. And the red dots, hopefully you can see the small red dots, that's the location of the pylon. So they are kind of at the risk of being hit by large ships. And also, for a structure of this type, it is important to sort of project or to forecast what would be the future shipping traffic, in order to make sure that, since this is a probabilistic analysis, then to make sure that it's still safe towards the end of its service life. So the next slide, and I'll just start the animation, because there you can see what happens when a ship hits the pylon to the left. And to the right, you can see sort of the scale of a container ship compared to the footprint of the tower. So the ship is huge, even compared to a tower as big as Chanakala's tower. So the lower part of the pylons are reinforced so that they can take the ship impact. So the lower 30 meters of the towers, and of course the pylon foundations, are designed for the ship impact, and that is the governing load. So you can see here for the tower foundations, there are some tie-back arrangements to make sure that we can transfer the forces. The tower foundations themselves are a little bit different between the European side and the Asian side, but it's both fairly soft, mud, clay, and sand. And it was necessary to improve the soil, and that was done by inclusion piles. So what you see on these two plots are the inclusion piles, and they are sort of open-ended piles. And then what the main purpose of them is really to reduce the settlements and to increase the lateral stiffness. So you can see here on these plots, you can kind of see the effect. With the inclusion piles, the blue lines and the dotted lines are without inclusion piles. So they make a huge difference to the stiffness of the foundations. Then moving on to aerodynamics, this is very much based on the learnings from stonecutters. So knowing where to be careful, where to put extra attention and focus on the investigations was really useful in these studies. And you can say on stonecutters, as you recall, it's a twin deck, it's a split deck with a monotower pylon. So it makes a lot of sense. Basically, the gap in your deck corresponds to the required diameter of the tower. Here's a little bit different because it's an H-shaped pylon. So any unnecessary increase in the deck has a significant knock-on effect on the pylon quantities and the cross girders in the pylon. So there was a lot of effort put into optimizing that air gap and keeping it as small as possible, while at the same time, of course, fulfilling the requirements to the critical wind speed. And this is just a list of the various places where wind tunnel testing was carried out. The large models were tested in Canada. There were testing carried out at Forza Technology, which is close to our office, so very convenient for the design team. And also in China, where the full bridge model was tested, because it requires a very, very wide boundary layer wind tunnel. And here comes perhaps the biggest challenge. If you ask the design team, they will say, forget about the technical challenge, this was the challenge. It's a very compressed design schedule, basically only 15 months to complete the detailed design for a world record suspension bridge. We started by being granted 2 months to review the tender design that had won. And it was basically just head on doing the detailed design. And of course, lots of activities had to take place in parallel in order to make that possible. In all fairness, I would say the contractor was equally aggressive with his own construction schedule. So starting in April 2017 and opening to traffic on the 18th of March this year. So very accelerated time schedule. And in order to do that, a lot had to be prefabricated to avoid time-consuming fitting on-site and weather-dependent operations. So similar to the Osman Ghazi Bridge, the towers on Çanakkale, they are in steel. Of course, it helps for the seismic as well to keep it as light as possible and as ductile as possible. But it is also to speed up the construction. So it was a mix of bolted and welded details. So the stiffeners on the inside are bolted and the skin plates are welded. And we made some careful analysis to help the contractor accelerate so that they could continue installing blocks before they had completed the welding. So since the towers are obviously on the critical path, that helped a lot on achieving the construction schedule. And then another thing, and that was a bit of a leap of faith for us, we decided to go into BIM for Çanakkale for the first time for such a big project. It was not a requirement from the owner. It was not a requirement from our client, the contractor, JV. It was something we decided to do because we felt it was the right thing. We felt it was the right way to all the time control the quality, control the geometry, and make sure that we captured all the changes as they happened. So it was, you can't call it BIM. It was 3D modeling, but it was really the first experience that we made. And gradually it gave us the appetite to also integrate it with our in-house program, Find Element program. So today they're actually much more integrated and they speak to each other. And it's just so much easier because we control the code of the Find Element program in-house ourselves. The only thing we didn't draw in 3D was the towers, and it was simply because of lack of resources. And we regretted it ever after. We would have wished we had the towers in the 3D model as well. But it came very handy at a point in time where there was a need from, although there was a request from the contractor side to accelerate on site. I'm not saying they were delayed, they could just see that they needed to speed up construction. And a particularly critical detail was the plinth. So the connection between the tower, the pylon caissons, and then there's a tie beam, there's a plinth and a tie beam, and then the steel shafts can start being constructed. As you can imagine, that's a very tricky detail because you have the concrete meeting the steel, there's the permanent works, there's the temporary works. And it was to a large degree based on in situ processes, and they wanted to go prefab. So we had within 2 months to change the entire construction method for that very, very busy detail. And we couldn't, I just say, we couldn't have done that if we hadn't had our BIM models already available. And they became very useful in the communication with the construction team on tolerances, on sequences, and on what temporary works needed to be there and when did it need to be cut out. So I would say for us, it was a fantastic learning journey, and we haven't regretted a single moment, even though there were some frustrations on the team. Yes, this is what it looked like on the opening date. You will say it doesn't look quite finished. You can probably see a tower crane or two, and you can see the catwalk. It is still there. So it's just to illustrate sort of the pressure and the urgency of opening to traffic and starting getting the toll money flowing. And therefore, all these temporary works are still there. The procedures for taking it down are in place. It will require some lane closures from time to time, but that's just the reality of having a bridge that is under a concession. Good. Then let's move north to Norway. Are we still okay again?
Yeah, we're good.
Good. Don't want the bus to be leaving for the boat without us. Floating bridges. This is a picture from a famous place in Norway, one of the very scenic fjords. And as you can see, if you just sort of continue the slope of the mountain, you can kind of imagine how deep it is. And it is very deep. This is Bjørnafjord, just south of Bergen, the second largest city in Norway. It's a stretch of almost 5 kilometers, and for 4 kilometers, it's over 500 meters deep. And this is the easy one. They have several crossings. This is the easier one, so that's the one we started with. Some of the fjords are up to 1.2 kilometers deep. So we'll need all the innovation and technology we can find. So why do that? Well, if you look at the green line, that's a highway from the south of Norway up to Trondheim. And 60% of Norway's traditional export value comes from this area. And today it's serviced by 8 ferry links. It's weather dependent, it's slow. And you can imagine sort of the socioeconomic benefit of reducing the traveling time from currently 21 hours to 11 hours. So there is a huge investment in Norway to sort of provide fixed links for all of these crossings. And the only way to do it in many of the cases is to provide floating bridges. And now that's not entirely new technology. There are a number of floating bridges around the world. Norway has 2, North America, they have some in also other parts of the world. So this one opened in the early 90s. It's about 1 kilometer long, and it's fairly close to the surface of the water, as you can see, in order to keep the center of gravity as low as possible. But what you see there, the concrete, that's actually floating pontoons, and you can see it during the installation at the picture at the bottom. So it's basically floated in one big piece. So that was the basis for looking at various ways of crossing the Bjørnafjord, so this 5 kilometer crossing. And there were 3 different concepts studied. The first one was a curved cable stayed bridge where the cable stayed span is placed on land. The other one is a 3-span suspension bridge, which is adopting tension leg platform technology from the offshore oil industry. And the third one is quite a fancy one. It's submerged floating tube bridge. Some people call it tunnel. We prefer to call it a bridge. And the challenge here for the 2 ones above the water is that there's a requirement for a 45-meter vertical clearance for navigation over a length of 400, 500 meters. And that's, of course, different to the existing floating bridges that are maybe placed 6 meters above the surface of the water. This one is 45 meters up in the air, so the center of gravity is something completely different. So that was a challenge. And one of the first things to look into is, of course, since it is so deep, the ships can sail anywhere. And they do. They do even in this shallow 50-meter water. That's shallow 50-meter water depth. There are also ships everywhere. So there were some quite sophisticated analysis of ship impact and of what happens if some of the cells in the pontoons are flooded, and what happens if we lose a pontoon. So that was a very important analysis, providing a lot of input to the early studies and the arrangement of the spans. And then also the construction, how to get these floating bridges in place, because they may be stable when they're installed, but they're not particularly stable in the temporary stages. So it was inspired by the Bergsøysund installation process, so one big curved piece assembled somewhere where it's relatively still, if you can say that in northern Norway, but it's not too harsh, at least. And then how to ensure the welding quality, trying to connect these pieces that are moving up and down. That was quite interesting. The tension leg platform is even more exotic, you could say. It is borrowing from the offshore industry, where they have offshore rigs on similar water depths as we are facing on the Bjørnafjord bridge. The 2 central towers are on floating pontoons, so they're steel towers in order to keep them light. And then the 2 ones at the ends, they are on fixed foundations, so we imagine that they could be concrete towers. This one had a top cable to stabilize it. We're still debating with ourselves whether that is a good idea, because it's very difficult to get it installed. But in the permanent condition, in principle, it is a good idea. And this is what the foundations could look like. So these tethers, they are pre-tensioned steel tubes. So they are tensioned during the installation process. And the anchors, they can be either suction anchors, as shown here, or it can be gravity anchors. It depends on the soil conditions at that place. Unfortunately, they are susceptible to underwater landslides at this place. So foundations is a big challenge. And of course, there are lots of uncertainties designing something as novel and innovative as a floating bridge. So the team used this uncertainty log to help them decide sort of the level of maturity of the technology. So basically, they were looking into, is this known technology, and how proven is it? And is it known within infrastructure, or is it known from another industry? I mean, one big difference between the offshore oil industry and infrastructure is that typically the platforms are designed for maybe 25 years or 40 years design life, whereas a bridge would have at least 100 years design life. So in principle, you need to find a way of replacing a lot of these elements, like the tethers. How do you do that? So that was a big part of the job. So thinking ahead, not just how do you get it installed, but also how do you maintain it and replace critical components. And then, interestingly enough, now we are exporting the technology back into the energy sector, because we're taking it from the fossil fuels into some concepts for infrastructure. Now, in the offshore wind industry, they're looking into wind farms at even deeper waters than what we know today. So in order to benefit from the really good wind climate for energy production at these sites, then they would also need to use some sort of floating structures to support the offshore wind turbines. So very interesting collaboration. We have a lot of collaboration across right now between the bridge team and the energy team. So some concluding remarks on these fantastic long spans. I mentioned Messina a couple of times, so this is the first time I actually show it. The Messina Strait Bridge, I think, is a dream project for some, a nightmare for others. Definitely, it was stopped some years ago when the president in Italy was no longer Berlusconi. But it was carried through until a complete detailed design. So we know at least it's possible to design a bridge spanning 3.3 kilometers, carrying both road and railway. And the Strait of Messina is also experiencing large earthquakes. So even though it hasn't been constructed, and that's of course the ultimate test, constructing the bridge, that's where we get the real learnings. And definitely speaking for myself, that's where my biggest lessons learned was from the construction process of stonecutters. But it has been designed, and a lot of the learnings have been implemented in projects later on. So I think it just illustrates the importance of keep pushing the boundaries and keep investigating and keep exploring, because even though it may not be implemented today or tomorrow, but we just learn so much from it, and we really improve our technology and our understanding. So that's a takeaway from me. And I would also say that Messina may not be constructed sort of in the near future, but we are looking at bridges that will beat Chenakle in the not so distant future. In China, they're planning suspension bridges that are even longer. In Nanjing, if we get to go to Nanjing in September, they are in the first phases of construction of the Chang'an Bridge, which will have a main span of 2.3 kilometers. So even though Chenakle was the first one to break the 2-kilometer barrier, then it won't have the record for long. And in the south of China, they're designing a double-decker suspension bridge, 8 plus 8 lanes, so 16 lanes in total, spanning 2.118 kilometers. That's perhaps an even bigger challenge, I would say that one. But it's not all world records. I think if we have the time, I would like just to spend a few minutes presenting you to this one. Are we okay? Good, it's just 2 slides. Because it really sort of closes the circle for me, at least. So while the floating bridges have been started in Norway, while Chenagale has been constructed, and while the world has been in 2 years of lockdown due to COVID, in the Philippines, they have also made a remarkable achievement, I would say. This is the Cebu-Cordova Link Expressway. You will see some similarities with stonecutters. I guess you can guess who's the architect. It's the same architect as on stonecutters. So some inspiration. It is the longest and the tallest bridge in the Philippines ever. And for them, it was a major milestone having this project completed. It's a toll road approximately 9 kilometers long. So it has this main bridge, which is a modest 390 meters, but with a 51-meter navigation clearance. And then some quite complicated ramps and then the access viaducts down to a causeway. And as you can see, it's traveling through a really beautiful area with mangroves. And I think it's just amazing to see a country like the Philippines, and with all due respect, with the level of skills and in the middle of a COVID lockdown, that they are still able to complete a project like this in 6 years. It shouldn't be compared to Chenagale, but it's still an achievement. And they had 2,000 workers isolated on the construction site for half a year during the lockdown. It was the only way they could do it. So this is what it looks like at night time. And that takes me to the final slide. And now I was hoping that I could embarrass Ian a little bit. But this is a reference for me. And we talk a lot about sustainability, and it's not just carbon and quantities. It's also the aesthetics. And now I mentioned architects a couple of times. I know there are also architects in the audience, and I could mention some of our collaborations. But I think it is important that we also consider that our bridges should be beautiful. They're standing there. They are part of the built environment for 100 years, and coming generations, they will look at them. So I think it is important that we make an extra effort. It doesn't have to cost additional money or additional materials or anything. It's more about the effort and the good collaborations, I think, and benefiting from people who are actually experts in their field, which is designing beautiful structures. So if you haven't watched this TED Talk, I would encourage you to do so and be inspired. So yeah, that was all for me, and I would just again encourage you to stay active in IABSE. It's a wonderful synergy with what you're doing as structural engineers, and do reach out. I'm sure everybody from the executive committee in the British group, or reach out to myself. We're more than happy to discuss with you how you can contribute, and if you have ideas, please bring them forward. Thank you very much.
Tina, thank you, and no thanks for the embarrassment at the end, but I suppose I get a copy of that slide. Tina, thank you, that was fabulous, and for those of us who work in the long span world, it's been something really special to see some of those projects. We have time for some discussion before we have to head off to catch a bus to get a boat, so please do put a hand up. There is a microphone, but I think probably if you can do it without, just shout from where you sit. If I can't hear you clearly, I will come with a microphone in hand. But it just says you're going to run around the room. In fact, yes, come on, David. I shall give David the microphone. He can run around the room if we did. But do, please, who'd like to start? Who'd like to kick off with a question for Tina?
Should we put some lights on?
I'm going to put the lights up so we can see you as well as you can see us. Who'd like to kick us off? Question or comment from anybody? Right at the back, please. Shout it out.
Hi there. I just had a question around design life, and you saying the ambition for longer design life, 100 years, 20 years, and what that means for sustainability. And I'm just thinking how do you design your bridges to be that long with so much uncertainty into the future, not just around climate change, but also around modes of travel? And I'm thinking, coming off the back of COVID, how the way we travel, or at least the way we communicate, has been digitized to some extent, and that would not have been accounted for. And is there any space for bridges to be more modular and to be more adaptable, say in 50 or 60 years' time, to adapt to what that mode of transport might be, or what that climate scenario might be?
That's a great question.
That's an excellent question, and difficult to come up with a sort of short answer. I think what you're pointing at is really sort of what is our mission as engineers. I mean, that's really the challenge in front of us, to try to use what we have, the codes and standards, but they were also based on something that was the best knowledge at that point in time, but it's not necessarily projecting 100 or 200 years into the future, in particular not with the kind of speed of development right now. I think we need to look at all factors, and you quite rightly said sort of modular construction, something that can be easily replaced, maybe also building some additional capacity into our structure. I mean, I have been part of some rehabilitation jobs where everything was at 100% utilization. It was literally impossible to do anything for that structure. So thinking about where, in a clever way, thinking about where would you put additional capacity so that it enables future generations of doing more with the structure. And it's not putting it everywhere where it's not needed, but the critical details, like the nodes and the connections where, you know, all the concentrated forces are come, okay, should we do a little bit extra here? Or should we consider an additional deck on a bridge? Or should we consider that one day perhaps the hard shoulders will actually be used for traffic lane? I mean, there are lots of things where we, together with our clients and the infrastructure owners, we can have that discussion of what is meaningful to do today, what is meaningful to try to plan for, and what is simply too expensive to include now. But it's being mature enough to have that discussion of sort of the initial cost and the cost of operating the structure and the cost of upgrading it. Would be my attempt at that. Ian, I'm sure you can supplement.
Well, I guess part of the answer is to do with those bits that actually can be replaced or upgraded, because there's several elements, for example, the suspension bridge, that are very difficult to change. Main cables, for example, foundation. These things are difficult to change, whereas some elements you can. So there'll be different answers to different parts of the structure. But that's a great question, and it's a constant challenge. It's something which we're all this much more aware of now, thankfully. Yes, please.
Three great options for Beyond Fjord. What was the client's view on the three options? And did they favour one in particular, or are they still all three under consideration, or where's the sort of the bridge owner's view of that?
Just before you answer, can you hear that at the back or not? We can. Okay. If not, I'll use the microphone. But the question is about the three Beyond Fjord solutions.
Yes.
Okay.
Very good question, and I think we're in the middle of that process. The first one to be ruled out was a submerged floating bridge or floating tunnel, because it was simply too expensive, and there were also some concerns with sort of the risk. I mean, if something happens, it's difficult to imagine anything than a major disaster. So that one was parked. It's still a very interesting concept, and there have been quite a lot of studies into it. So I think feasibility-wise, it didn't fail. It was actually confirmed as feasible, but partly because of the uncertainty log. There were too many components that were not tried before. I know that both the Koreans and the Chinese are still doing a lot of research into that option. The next one to be ruled out was the suspension bridge. So the floating suspension bridge with the tethers, yes. Also, again, partly because of the cost and partly because of a little too many unknown parameters. So the one that will be taken forward, if anything is taken forward, it's a curved cable stay bridge where the tower is placed on land. And we were so fortunate that there was an outcrop where it was possible to place the main tower and therefore have the navigation span, because if that wouldn't have been possible, we would have had 2 floating towers, and that was also a major challenge. And one thing we discovered, and that's common for all these concepts, is that they behave completely different to what a structure on fixed foundations would do. The movements are so slow. So resonance is with completely different frequencies than you would normally consider. So yeah. But we're still waiting for the Norwegian road authorities to give the final go ahead for the next phase. So we were told last year it could have been in September. Now we're expecting it perhaps after the summer holidays, but we don't know.
While you're thinking, I'd love to ask a question about the wind climate studies you did in Stonecutters. Several of us in the room have had some involvement with the bridges in Hong Kong over the years, and indeed developing the wind climate models. Did you find that as a result of the studies you had to change the requirements, critical wind speeds and so on, from the structural design manual that were sort of set down?
There was a project-specific design manual, which is somewhat different to the structures design manual in Hong Kong. It was more severe, and it was mainly because the turbulence level was higher than what the codes had predicted. The requirement to critical wind speed on Stonecutters is 95 meters per second, as I'm sure you recall. And we're seeing in that region, we studied some crossings of the Pearl River Delta, which is not too far away. And our recommendation, based on more recent knowledge, is that because the wind climate has a tendency of becoming more extreme, that we would recommend that we should go a little bit higher than that. Yeah. Yeah, and also, I mean, it's also more unpredictable. The Cebu Bridge that I showed at the end, normally the typhoons wouldn't come so far south in the Philippines, but it got a direct hit in December. Fortunately, the main span had been closed at that point in time, but it was up to the full design wind speed of 250 kilometers per hour. So we had measurements on the deck, and it's not normal to have typhoons of that strength so far south in the Philippines. So there's definitely a change.
It kind of gives us a bit of confidence, doesn't it, when we withstand that kind of...
It was a full-scale test.
Okay, now, who else? Questions for Tina? Yes, please.
It's interesting to see where floating foundations could go. My biggest fear of my bridge is by getting back to them to maintain them. But my limited experience of stuff in waters, it becomes habitat quite quickly, and particularly floating. And if you go into warmer climates, how would you prevent or maintain those?
Good question, and I don't think it has been thought through completely at this point in time. Right now, we have been involved in the studies in Norway, which is cold climate, but it doesn't prevent the mussels from growing everywhere. So you're absolutely right. If you wanted to move that technology, say, to the Red Sea or to the Philippines, definitely something to consider because it adds significant weight.
Be a deliberate design, wouldn't it? The modern sustainability biodiversity kind of...
Or you arrange a restaurant on one of the pontoons.
Anybody else? More questions? Comments? I can't believe you started with the silence. Mark, please.
I'll ask one. Hi, David. Thank you for mentioning Lionsgate and Stormwell, all Chingmar, even all the old projects that I remember. I was having a tear-away almost. I was interested in the design program for or schedule for Chinakli was very short. Was that helped by some of the team members working on the Izmit Bridge before, the Osman Ghazi, or how did you achieve such a tight schedule for that? It just seems the demands of clients are ridiculous these days, and it's just, I think you must have had a lot of people involved in Izmit, also involved in Chinakli to help achieve that. And, with all the problems you mentioned as well, ship impact, for example, protecting the towers, reinforcing them instead, and justifying all that. You know, things like that take time and effort to do and convince the client to go along with that.
ISMIS was definitely a solid foundation for it, because it's not that long ago that ISMIS was completed. So you're right, we were able to take that design team and then continue on Chinakale. But of course, there are some differences between the two projects. The seismic actions at ISMIS are a lot higher than on Chinakale. But on Chinakale, because it's such a long span, we have the twin deck, which is a challenge in its own right. It's also, I would say, it's very much down to the collaboration. I would mention teamwork again, and building that level of trust between the end client, the owner, and the independent checker, and the design team and the contractor, constantly having that dialogue about what are the critical decisions to make, what do we need to agree on early, because otherwise it will derail everything further down the road. And I would say from our perspective, there was a really constructive dialogue between all those parties, and that helped a lot. And then just having, I mean, one of our, the chief designer for the foundations, he also designed the anchor blocks on Great Belt. So there is also a lot of experience and knowledge and legacy and just knowing what works and what doesn't work. He didn't have to go around in loops and redesign. He could fairly quickly sort of zoom into the right solution, which was to move the anchor blocks. So yeah, so I think the answer is all of the above.
Angus.
Yes, the issue of replaceability of suspension cables. I mean, I think my understanding is that you believe that we've learned there have been an awful lot of suspension bridges that have had corroding cables. In general, there is faith that with dehumidified air blowing through it, that you should be okay. But in 150 years' time, when a client wants to know whether they can get another 150 years out of the bridge, have you any idea what they will do?
I think, as you quite rightly say, I mean, dehumidification is one measure that we put a lot of confidence in, but I think also having instruments built into the cable so we can monitor them, I think will be even more important. Using that perhaps in combination with a digital twin, so that we all the time have a good grip on what is the current sort of health status of the structure, I think is also important. And then finally, I mean, it is not completely impossible to replace the main cables. I can recall at least one example where we did it. That was the Pont d'Aquitaine in Bordeaux in France, where there was simply constructed sort of a plinth on the pylon top, and a new set of saddles were placed there, and the new main cables were placed outside of the existing cables. And then yes, Tankerville perhaps also, yes. So it is possible. Of course, it helps if the original designer did think about the scenario and made enough space for it and so on. So I think your point is something very important, because the main cables, that's the most difficult thing to replace, and the anchorages that are cast into the huge, massive blocks. That is difficult.
One more. Yes, please. Right. Thank you.
So you mentioned the introduction of EIM modeling and digital twins, the design, and you showed a lot of parametric analysis that probably took place during the design of those bridges. And today we talk a lot about the AI revolution, the big data revolution. Do you think we're close to a moment where a lot of the decision, or a significant part of the decisions, will be made using those technologies like computing? So instead of having a human run 100 different parametric models, have a computer do it, and then eventually decide.
I think that's a very interesting question. I mean, AI and machine learning is definitely something that we are looking into as part of the process. And if you have a lot of options to run through, or a lot of sort of comparisons to make before you make a decision on what is most optimal, then definitely I think it can help us. I mean, basically what we want to do, we want to We want to let the machines do the boring and repetitive work, and then let the engineers do the intelligent part of the work and make the critical decisions. So I think with a careful design of the processes and using these modern technologies in the right way, then definitely I think it can help us, in particular in the cases where we need to compare a lot of different options. But I wouldn't underestimate sort of natural intelligence as well. And engineering judgment and structural understanding, and I think that's that's basically what still makes us relevant as engineers. So I think taking the full step and relying 100% on those technologies, I think there's still a bit of way to go.
Well, on that very sobering note, I think it's a good moment to draw to an end. Thank you, Tina, so much. Really lovely, wonderful sort of trip round some of the great bridges. Many of us in the room know the bridges you're talking about, of course. They're sort of headline grabbers. But thank you so much. And also telling us something of your story, both your COBE story and your IABSE story, which is interesting to see and for many of us to understand. So thank you. A lovely kind of combination of some really interesting little technical insights from your experience, and also just a wonderful sort of oversight of how these big projects come about. They are extraordinary, and they do tend to take a long time. But we've heard from you on some of these really spectacular ones today, and particularly to hear about Chinakle, which I think many of us have been longing to hear about. I'm fortunate enough to have heard about it already, but I know that others haven't yet. So thank you so much. Those of you who are coming on the boat will have an opportunity, of course, to quiz Tina even more closely. I promise not to pin you again for the whole meeting. But thank you so much, Tina, for really...
Thank you.